Good evening, Precalculus. Welcome to another exciting of Math with Dan. So today we're doing 8.1.4. So we're talking about finding the area of a circle and estimating an approximation of pi. Now, the way that Archimedes did this is he had both a circumscribed and inscribed dodecahedron, and sort of found the areas of these two functions and sort of used it to figure out what pi was. So, or in terms of the circumference and, well, yeah, area, in terms of pi. What we're going to do is we're going to take, we're going to sort of go through the same method and figure out how to do it. Now, this is sort of one of the more difficult things to do when it comes to mathematics, is sort of doing the squeeze on these two ideas. So we're going to go through 48 and 4-49 together. So what we have here for the inscribed dodecahedron. Now, when we sort of look at this, we see, like, first question we want to ask is, what is the angle of each of these objects, of each of these triangles? So since it's a dodecahedron, that means it has 12 triangles. Did not mean to do that. Oh, I thought I locked it. I did lock it. There, now it's locked to the background. And so we're squeezing pi, so if we think about it, there's 12 of them. Double check, you can count if you want, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What we're going to do, so since there's 12 of them, we would just basically do 360 divided by 12, which equals 30 degrees, is what each one of them are. Now, what happens is over here, given the radius is 1 unit, so in this case, the legs of our isosceles triangle are 1 unit, it wants to know what is the height. Well, think about it in terms of our identities. If this right here is 30 degrees, then if we take sort of the smaller point and we just sort of take one of these triangles, and then this would be 15 degrees. And then if we sort of turn ourselves sideways, we could sort of think of this as sort of our x, and then this would be our y. So if we think about it, we have our unit circle, so we have our x value, we have our angle, and we have our radius. Well, wouldn't sort of cosine, let me actually make this a little thinner, cosine of 15 would equal adjacent over hypotenuse, so x over 1. So I guess it just means x equals cosine 15, which means that this length is just cosine of 15. So what we would have is just cosine 15, and we're going to leave it as that because what we're going to see in a moment is some nice cancellations that we can use using some of our trig rules. And then so for the base of each triangle, well, since it's y, we just use sine, so sine of 15 degrees would equal y, like opposite over hypotenuse, so y over 1. So therefore, y equals sine of 15. That's for half of it. So technically, the base, if we had this as y, would be also y, and so therefore the whole length of this would be 2y. So the base of each isosceles triangle would be 2 sine 15. Now what we need to do is find the area of each inscribed polygon. Now one of the quick things we can do, we can actually just we have both the height and the base for each of these triangles. So what we can do is actually just sort of apply that and find the area of one triangle and multiply it by 12 to get us the full area of our object we have. So the area of our triangle would be, we would have 12 times 1/2 times height, so 1/2 times our base, which would be 2 sine 15 times our height, which would be cosine 15. Now, if you remember trig, some of our double angle formulas, if we remember that, then you'd remember that sine of 2a equals 2 sine a cosine a. So right here we have 15 and 15. We can actually sort of combine that, and we'd end up have 6 times, or I should say, let me actually go through all of this because I'm sure some of you would be confused. We have 12 times 1/2 times sine of 30. Now sine of 30 is just 1/2, so we'd end up with, because if we look on our unit circle, that's what we'd get there. And so when we calculate this, we would have this become 6, and then this is 1/2, so we end up with 6 times 1/2, and then we'd multiply that again, end up with 3 as our area. So we end up calculating the area of this dodecahedron inscribed in our circle as an area of 3 units squared. Now what we'll do is we're going to go ahead and continue on to 4-89, and we're going to find the area of a circumscribed dodecahedron. So I'm going to go ahead and just sort of erase some of the markings here. One of the benefits of video capture is that you can always just go back and double check that, so no mistakes, just happy little accidents. In this case, we have a slightly different thing going on. Our triangles have the same interior angle, however, our height is now 1 instead of our legs being 1. So what we typically do is we do a similar thing. So the base of each isosceles triangle, we could use tan if we wanted to, but I don't think we necessarily do, or do we? I suppose we could. Yeah, that makes sense. Alright, so the base of each isosceles triangle, actually, hold on a moment. So, with this version, we have our 1, which will be our x, so we can just sort of call that x, and then this would be y. And similarly, each triangle would have an angle of 30, but what we do is this would then be 15 again. If we use our tangent, we would have tan 15 equals y over x, which means y equals, well, x is 1, y equals tan 15. So that would be the length of 1/2 of it, but as like the first example, it would have to be 2y, so the base of each triangle would be 2 tan 15. So given the height of each triangle is 1 unit, so this right here is 1 unit, find the area of the polygon. So well, we just do the same exact thing. So we have 12 triangles, and then we'd multiply by the area of a triangle, which is 1/2, times the base, which in this case is 2 tan 15, and then times, which in this case is just 1. So when we do it all out, we end up with 12 tan 15. Because the 1/2 cancel, so you end up with just 12 times tan 15, so you have 12 tan 15. And when you actually calculator, because there isn't a pretty thing for that, you end up with a value of approximately 3.125. And from here, oh wait, no, not 3.125, 3.215, sorry. Momentary math dyslexia. And so when you do this, if you look between these two things, since we know the function for the area of a triangle, of a circle, is pi r squared, based on just this little mathematical proof, we've sort of proved that pi is greater than 3, but then at the same time is less than 3.215. Now, what we would do from here is we're going to sort of work a little bit further. And then in 50, what you're going to do is rather than dealing with 12 sides, you're going to deal with n sides. And what's going to end up happening is you're going to be able to put a squeeze as you on pi as you increase the number of n, and you get a more and more accurate answer. And so that's what's going on today in our math lesson, and we'll sort of continue from here. Tomorrow we're going to be looking as those n to infinity, what happens with some certain types of functions, but this is pretty much what we're doing today. So, I hope this helps you all. If you have any additional questions, I'm always available on the Discord or through Zoom or email, but that's what's going on.